Hey everyone, how's it going? We're going to cover our estimation of cardiovascular endurance capabilities lecture today. Um, the one thing to keep in mind is it's a bit of a continuation of the cardiovascular endurance test that we've covered already. It explores a little bit more in depth the reasoning on some of the assumptions that we make about these tests in order to find the results or get the predictions that we have. But it also explores a little bit as to why, or more specifically, how we apply these tests in a real world setting. So to get started, again, I want to go over these assumptions, and this would be a very, very good slide to know, I think, both for your lab, but also for your lecture sections as well, because we cover it in lab. So when we're using our VO2 max tests, a lot of the time we need to use submaximal exercise and submaximal test conditions. One of the main reasons is it's really, really challenging to actually get someone, in particular someone who's not trained or hasn't done a lot of exercise, to actually reach their maximal effort. So reach max heart rate, reach VO2 max. And even for well-trained individuals, day-to-day reaching that maximum can actually be quite challenging and might vary a bit in and of itself. So the other point to that being, that maybe unfit individuals or sedentary individuals, so people that haven't exercised very much, might also potentially have an underlying cardiovascular condition or a medical condition that isn't apparent yet. So getting these individuals to do a maximal effort bout of exercise when they haven't done so maybe ever in their life is potentially risky. So to avoid risk or harm to your client or patient, depending what setting you're in, it's better to do a sub-maximal VO2 test. So that avoids having to exert yourself fully. Okay, but in order to do that, we need to make a few assumptions, and we covered a lot of these principles so far and have reviewed them a couple of times. We'll do that again. So when we're looking at the relationship between heart rate and VO2, and to some degree, again, if you recall, you can think of your ventilatory rate, that there is a general linear relationship there. Now, we know at a certain point in time that when we're talking about, say, our ventilation or our lactate, there's that sharp inflection up once we hit our anaerobic threshold. But generally speaking, these two have a very linear relationship, okay? So that's one assumption. Again, if these assumptions are broken on an individual basis or not reached, the submaximal exercise and its predictive power to state with some assurance what the maximum VO2 is for an individual, or what their maximum aerobic capacity is, right? It's saying the same thing. Then the whole system kind of falls apart a bit. Okay, but we find these to be generally true. Okay, next assumption is that attaining a maximum workload indicates attaining a VO2 max. So we'll speak to this in a moment, but again, a lot of these graduated or ramp and aerobic tests where you slowly, incrementally increase the intensity, you do so by increasing the workload, right? Again, if you're on a treadmill, you're increasing the percent gradient or the speed. If you're on a bike or a spin bike, you're increasing the resistance or the amount of watts or the power output that you are doing. So all of those are ways to increase the workload. So when you reach a maximal there, or head towards a maximal in these submax tests, we have to assume that that will indicate your VO2 max. Okay. Next is that steady state heart rate is reached at each of these workloads, or again, as it notes here, probably more importantly, that it's consistent from day to day. So what can happen, and there's a lot of research behind this now, is our heart rates can actually vary quite a bit from moment to moment, day to day, depending on what sort of stress our system is under. Now, if you've done a little bit of research or digging around in health and fitness of late anyways, it's become quite popular to talk about HRV, so heart rate variability. And what that is the millisecond to millisecond differences in heart rate that occurs. So, and typically you want it to be very variable. Okay, so the more variability that your heart has in milliseconds beat to beat, the better or the more responsive your nervous system is to your body's needs and demands, and that's a good thing. So what you'll find is your heart rate variability will be low. You'll have a low number if you're really, really stressed, or if your sympathetic nervous system is really overriding your body. Okay, so with that extra stress, that can be from recovering from training, having trained too soon, work, life, school stress. So all of this can actually keep our heart rate variability down, or HRV down, when we want that to be lower, to have more variability. So again, the steady state heart rate being the same at each workload day to day, that's not always true. Okay, sometimes you work out, your heart rate will increase if you're overtrained, or some of the other previous examples I made. Okay. Another assumption, so we're on our fourth assumption now, is our maximal heart rate for any given age is uniform or the same between all individuals. And again, while this is relatively true, it's based on a bell curve, right? So way back at the beginning of lab, we spoke about how, statistically speaking, when you're looking at a large population, most, like 50% of people are about in the middle of your statistic or variable, whatever you happen to be looking at, and very few people are on the extremes, right? And the more extreme you get, the less and less likely someone is to be there on any given variable as far as biological systems, and psychology follows a relatively similar trend. But yes, so when we're talking about maximal heart rate for a given age, we have these standards that are out. The old one is 220 minus your age is your maximum heart rate, and there's newer ones out since then, and different ways where you can talk about your resting heart rate threshold as part of what your maximum heart rate is. But the point being that we're making an assumption that if you are 20, that you have 220 minus your age, so your heart rate max should be 200 beats per minute. Okay, so that's an assumption that we make, whereas we know individuals from person to person will vary. If VO2 at any given workload is equal or equivalent among individuals, again, if you think of the ACSM equations that you did, that is a VO2 workload that we equate, and that is set. That is a set algorithm that we put in certain variables to, and we make an assumption that it is the same for everyone. Again, there is variability from person to person, but generally speaking, when looking at a population as a whole, statistically speaking, we can assume that this is true. Okay. Now, the last part is whoever happens to be participating in this particular test, they don't have any medications that would alter their heart rate response. So a very common one is caffeine. But again, depending on what sort of medical condition the person may or may not have, it will definitely alter heart rate. Okay. So again, these are very important assumptions to know and have known about our VO2 max or our aerobic tests. Okay. It's because we have these relationships, in particular the linear assumption between heart rate and VO2, that we can use heart rate, which is much easier to measure, is cheaper, the equipment's more accessible, it's a lot easier to use. And so between heart rate and VO2, but also with the steady state at a given workload. So if VO2 at a given workload is similar to heart rate at a certain workload, and we know the maximum of these two are assumed to be a uniform or equivalent among individuals, and there's no extraneous factors like medication weighing in, we should therefore be able to relate heart rate or max VO2 or max heart rate based off of incremental workload. Okay. So again, really important assumptions here. Okay, so when we go to apply this, we have a few different means we can do this. We have some for running, walking, and stepping. We also have one for cycling, and we'll speak about those, and we'll dive into how do we actually use these. Like, how do we go about this? So, if most of us around this part of the world, Vancouver, BC, Canada, we will have probably done a 12-minute run test some point in time in our schooling, most likely high school. And the idea is to see how far you can run. There are different mile tests or 1.5 mile tests, 12-meter shuttle test. We spoke about shuttle tests in the anaerobic section, and the Rockport 1 mile fitness test. Now, all of these use those same assumptions we were speaking about earlier: heart rate and workload. And they do that based off of our pacing. For example, if you remember the ACSM metabolic equations to give us our VO2 for any particular activity, we typically use pace. So a lot of these running tests will use pace as an indication to figure out your VO2. Now, your heart rate, you can use a heart rate strap and measure that. And when you correlate the two, as we'll see a bit later, you can get your max VO2 as a result. Okay. Very similar, we have step tests. Now, step tests are convenient because you don't need a lot of room. You don't need a lot of distance, for example. We don't need a track or 20 meters worth of straight running room to go back and forth, or a mile's worth of track even. We can simply have a step, so something like this. Now, this one of the more common, or I shouldn't say common necessarily, but one of the, I would say probably more suggested step tests to take if you're just going to try to find the cardiovascular endurance capacity of the population in general, so both sedentary and non-sedentary individuals, would be the Queen's College step test. Now, the reason for this is it doesn't take very long. It's 3 minutes. We have a standardized bench height, and this is lower than some other step tests that happen, and it requires less coordination than some other tests. So some other tests actually have you step up a couple steps and step down. Others have a bench height that's a bit higher. So for individuals that are shorter and or have aren't quite as cardiovascularly fit, it's easier to do this test. And so the general setup is you get up to this step. The test administrator has a metronome. So a metronome is just something that keeps steady timing with a beep. And then you're supposed to step on every beep that you hear. So it's up, up, down, down with your steps. It'll beep, 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 just steady. And for men, this is actually backwards on the slides, on the other set of slides that you have, but for men it's 22 steps per minute. Oh, sorry, no. It is supposed to be the other way around. For women it's 22, for men it's 24 steps per minute. And then that math will work out a bit better. But yes, and the idea is once you have this number of steps that are completed or stages, what you can do is you take your heart rate right after the test. So they say within 15 seconds. So the idea is about 5 seconds lapse. You take your heart rate for 15 seconds, so between second 5 and second 20. And then you multiply that by 4, just like you again did in your lab. And so you get your beats per minute. Okay. Now with that, you get to transfer that information. And same with these, I forgot to mention, what we do is we take our results and we apply them to a standardized set of norms. Okay. So just like you've done again in your lab, where you'll get a result and you look at a table at the end of the lab, and it will give you some sort of classification of fair, poor, average, great, excellent, that sort of thing, okay? And so that's how we figure out roughly what an individual's cardiovascular capability is, okay? We have another, one last kind of test to look at here. So we have our cycling or bike ergometry test. The interesting thing about that is it really comes down to the resistance on the wheel. And although it doesn't mention it here, I'll bring it up when we look at another table. But a person's body weight typically matters in these. So for example, larger individuals are going to be able to put out more watts or more power for any given workload than smaller individuals. And it's mainly due to muscle mass most of the time. Okay, and that's not a fully true sort of thing, but ultimately when you put cyclists out on the road versus on a stationary bike, the number that you look at closer to see what their capability is something called watts per kilo, so watts per kilogram. And the idea behind this is, again, if you have a lot of body weight that you got to carry around with you on the bike, you should ideally have more power. But relatively speaking, it might not be as much as another individual who has the same amount of fitness, is maybe smaller in mass or weight, and can also put out a relative same amount of power, again, relative to their body weight as a ratio. Okay. But I digress. So again, we can set our workload on two different variables here. So I was saying power, so that in a similar way would be resistance to pedaling, or we can talk about cadence, which is the speed or how quick you're pedaling. Okay, and these things together generate watts. Sorry, I should be more specific about that. The resistance is just how much force is needed to pedal or push forward. Okay. Good. So with that in mind, here we are. Someone's taken their blood pressure mid-test here, or heart rate, just to make sure it lines up with the chest strap, I guess. But I wanted to go over just a few examples of, if I can find this, of how we can look at some of this data. Okay, so if we look across multiple, there we go. That's what I wanted. We look across multiple types of aerobic tests to try to measure VO2. Okay. What we see if we look at, this is like a clinical study that was done to look at stress tests in a medical setting. But the idea is they're trying to relate, for example, the oxygen costs, so VO2, for different patient populations, give them a functional medical standing, if you will, standard. And then again, relate that to how many METs, which if you know someone's workload or VO2, you can convert to METs fairly readily. If you're on a cycle ergometer, how many watts that is for someone roughly around 70 kilo. Here's our Bruce protocol. The Naughton we did not do. But again, METs you should be familiar with. So the idea here is, if you look at this graph, we can see whether we use a cycle ergometer or our Bruce protocol, that at certain levels, certain amounts of workload that has been incrementally added on relates to a certain amount of MET increase, which equals a certain amount of VO2 increase. Accordingly, we'll see people's heart rate go up across these conditions. Okay. So just something of interest to see that, okay, truly, we can figure out if someone cycles at 10 METs, that's the same as saying their VO2 cost is 35 milliliters per kilogram per minute. That's probably at the upper end of capacity for a sedentary or a non-active or physically active person. And again, we can see that Bruce 1, 2, 3 steps, not on the modified, but on the classic, equals about that point in time, maybe just slightly higher. And again, we can look at our METs there. Okay. So these tests can cross. Sorry, I just want to adjust the size there. They can cross relate to one another. But one of the other things I wanted to mention, as far as going back to the assumptions that you have to make in order for these to be true. Now, there's two different types of graded exercise tests that we can do, or incremental exercise tests we can do, and one is called a graded and one is called a ramp. And we might have seen these protocols in, if you recall, from the bulk and the Bruce. Okay. Now, one thing I want you to note here is we'll notice that the bulk has a fairly even one-to-one kind of workload to time kind of increments. Whereas the Bruce, we actually notice has a lower slope. Okay. Now, if you recall back to one of the assumptions we have to make about our correlation between VO2, heart rate, and workload, is they should all be nice and correlated and linear together. So one of the issues that can happen in a very high ramp based test is our cardiovascular system might lag behind the actual workload. So we might actually get through one of these tests without our cardiovascular system actually being able to handle that. And so we might get a little bit of a higher reading than expected, because we didn't have enough time to fully reach steady state cardiovascularly for that workload. And so that's why this is really important here, that we have that 3-minute time to stay at that particular workload. So arguably, the Bruce will potentially give a truer indication of your workload. Okay. But there is certainly research for ramp tests or ramp style tests that will also give information fairly reasonably. And sure enough, here we go. We have the bulk treadmill tests, and we can see that we have a set of standardized norms, just like all our other tests. And again, this is how we can gauge where someone's cardiovascular endurance capability is at, right? We simply relate whatever stage they got to, which was based on time. And again, here we can see we're looking at a women's set of standardized norms based on the treadmill, 12-minute run, 1.5 miles, again, bulk treadmill. So we can get a whole set of norms here. This is just an ACSM table. ACSM table that you can pull off the web readily. Okay, and so through all of that, it gives you a max O2 prediction. Okay, again, because of the assumptions we make of the relation of VO2, heart rate, and workload. Okay, all right. We'll just have a few more. So here again, just to illustrate the Bruce protocol, if you haven't seen it on a graph, we can kind of see that we have some time here to reach steady state as far as our heart rate. And we can say for sure, okay, when our heart rate is at this rate, yes, we are sufficiently happy that this heart rate is stable, it's set, and we can make a better prediction from this stage to that stage of the linear relationship of the heart rate as it goes up. Okay, so we can draw a very linear line if we wanted to, based off of the stages you get to, right? Because of that, we can also therefore correlate a very linear relationship in parallel with our VO2, and therefore get to our predictive max, which is again something you would have done in lab. Okay. Just to highlight again, stages, if we were to put them into our ACSM equations, we could put our speed, our gradient, and of course we can figure out what our VO is for that particular speed and gradient, and that is important when trying to calculate someone's VO2 max or predict it. Now, if we didn't want to go through all the calculations, there is another way. I think this is really important if you're going to be doing this more clinically out in, say, the real world. You can use this fairly quickly if you have a client present as well. It doesn't require any calculations. But again, based off of all the previous assumptions that we've listed already, all we need to do is look at our heart rate, whether it is a male or female we're working with. We put a little dot on this side of whatever their work or whatever their heart rate was. And let's say they got, so here's a step test based off their body weight, but we're going to ignore that and we're going to look at a cycle ergometer. And here's some kilogram meters per minute, which we could also have listed as watts. And so we take that dot way over here on their heart rate, and we put a dot over here on their workload. okay, for whatever test that happens to be, we essentially draw a line between the two. Okay, when we draw that line between the two, we're looking to see where that intersects here, because this middle graph is maximum oxygen intake. Okay, so on this graph right in through here, that's where we're looking, that intersection as it goes from pulse rate to workload. Right there we can see, okay, their maximum intake is a VO2 of 3.4 liters per minute. Okay, so it's just another way, it's called a nomograph. It's just another way that we can solve for the same results that we would for a VO2 max because of that linear relationship. Okay. Yeah, all right, so that is it for this lecture. Again, you probably noticed there's a lot of tie-ins between lab and lecture information now, but both should support each other as we're heading in towards the final. Okay, happy studies.